In this video, we're doing a couple more examples of graphing linear equations, including what it looks like to graph perfectly vertical and perfectly horizontal lines. So we're doing 3 examples: y equals 3x minus 5, x equals negative 3, and y equals 1. And as a reminder here, I have the slope-intercept form of the equation of a line, where, remember, m is the slope of the line, and b is the y-intercept, or the point where the graph intersects the y-axis. So if we look at our first equation here, y equals 3x minus 5, we can see that it's already in slope-intercept form. Our slope is going to be 3. If we just match this up to this form here, we can see that our slope is 3 and that the y-intercept is negative 5. It's really important to include this negative sign, if there is one, in front of the y-intercept. So the y-intercept is going to be negative 5, and we can just use those two pieces of information to sketch the graph of the line. We can also find coordinate points along this line by choosing values for x and then finding the associated values for y, plotting those points, and then connecting them to draw the graph. But with these two pieces of information, it's probably faster just to sketch it this way. So first we'll plot the y-intercept. That's going to be negative 5. So we're going to go down 1, 2, 3, 4, 5 in the negative direction of the y-axis. And then our slope, notice, is positive 3. Well, remember that positive 3 is the same thing as positive 3 over positive 1. It's also the same thing as negative 3 over negative 1. We're going to use these two pieces of information to sketch the graph of the line. So if we say that the slope is positive 3 over positive 1, since we know that m is change in y, or delta y, over change in x, or delta x, we know that positive 3 over positive 1 means go in the positive direction of the y-axis 3 units, and then go in the positive direction of the x-axis 1 unit. So we're going to go up 3, 1, 2, 3, the positive direction of the y-axis, and then over 1 in the positive direction of the x-axis. And we can keep doing that. So 1, 2, 3, and then over 1. We can also use the fact that positive 3 is equal to negative 3 over negative 1 to say that we can go in the negative direction of the y-axis 3 units and then in the negative direction of the x-axis 1 unit. So that would be down 3, which would be about 1, 2, 3, and then over 1 about right here. So we could keep going in that direction also. So you can see we have enough points now, and we can go ahead and sketch the graph of the line, which will look something like this, and say that that is the graph of the line y equals 3x minus 5. Now, what do you do when you can't find the slope and the y-intercept because we only have one variable involved in the equation? This is still a linear equation because we have first-degree variables. We have x to the first power, and we have y to the first power in this separate equation here. So it's a linear equation, which means its graph is going to be a line, but we can't put it in slope-intercept form because we only have one of the variables. We don't have y and x. Well, these are actually special cases. If we have x equals some constant, then we know we're going to have a perfectly vertical line through the point x equals negative 3. So here, x is negative 3. This is negative 3 along the x-axis here. This means no matter what the value of y is, x is always going to be negative 3. So I can go ahead and say that x is always going to be negative 3 like this, and then I can connect these points and just draw my perfectly vertical line through the points here. If you really want to prove to yourself that this is the case, you can actually put this in slope-intercept form. Because there's no y in this equation, to put this in slope-intercept form, we would have to write it as 0y equals, we have 1x here, so we'd say 1 times x, and then we have a negative 3 here, so we'd have to say positive 3, because if we simplified this equation, we'd get 0 equals x plus 3. Subtracting x from both sides, we'd get negative 3 equals x. We'd get back to our original equation. So in slope-intercept form, this is 0y equals 1x plus 3. Notice that if we try to plug in points for x that are not x equals negative 3, we're going to get something that's undefined, right? So we know x is always equal to negative 3. If we try to plug in x equals 0, we're going to get 0 times 1, or 0. 0 plus 3 is 3 on the right-hand side, and 0 times y is always going to be 0. So we're going to get 0 equal to 3, which can't possibly be true. So we know that the equation is undefined at x equals 0. What if we try x equals 1? Well, at x equals 1, we'll get 1 times 1 is 1. 1 plus 3 is 4. We'll get 4 equal to 0. That's also undefined. So no matter what value we plug in for x, except x equals negative 3, we're going to get something that's undefined because, of course, x isn't defined here at 0 or at 1 or at negative 1. It's only defined at negative 3. What if we plug in points for y, right? What if we say y is equal to 0? Well, at y equals 0, we're going to get 0 times 0, or just 0 on the left-hand side. So 0 equals 1x plus 3, or 0 equals x plus 3. 0 equals x plus 3. Subtracting 3 from both sides, we get x equals negative 3. What if we plug in 1 for y? Well, we'll get 0 times 1, which is 0. We'll get 0 equals x plus 3, or x equals negative 3. So no matter what value we plug in for y, we're always going to get x equals negative 3, which makes sense because if y is 1, x is negative 3. If y is 0, x is negative 3. If y is negative 1, x is negative 3. So we have this perfectly vertical line. So that's why if we have x equals some constant, then the line is going to be vertical. If we have y equals some constant, then the y is going to be horizontal through whatever point this is here along the y-axis. So we find y equals 1. Y equals 1 is right here along the y-axis. And so then our line is going to be perfectly horizontal through this point like this. If we want to prove that to ourselves, we can put it in slope-intercept form, and we can say y equals 0x plus 1, right? Because there's no x in this equation, so we would have to multiply x by 0. This would be y equals 0 plus 1, or y equals 1. So we can rewrite it in that slope-intercept form, and then we can do the same thing we did with this equation. We know that the equation is only defined when y equals 1, so if we try to plug in values for y that are anything other than 1, we should get something that's undefined. So what if we say y equals 2? Well, we get 2 equals 0 times x is just 0, plus 1 is 1, so we get 2 equals 1. That can't possibly be the case, so we know the equation is undefined here at y equals 2. What if we say y equals 3? Well, we'll get 3 equals 0 plus 1, or 3 equals 1. That can't be true either, so y is undefined at 3. And if you plugged in any other point for y, 0, negative 1, negative 2, you would get an equation that doesn't make sense. It would be undefined because y is only defined at 1. On the other hand, if we plug in values for x, we should always get back y equals 1. So if we start plugging in values for x, let's say x equals 0, we'll get 0 times 0 is 0, 0 plus 1 is 1, so we'd get y equals 1. And that makes sense here because at x equals 0, we know that y is 1. If we plug in x equals 1, we get 0 times 1 is 0, 0 plus 1 is 1, so we get y equals 1. So here at x equals 1, we see that y is equal to 1 right here. If we plug in x equals 2, we get 0 times 2 is 0, 0 plus 1 is 1, we get y equals 1. And if we do, let's say, x equals negative 1, we get 0 times a negative 1 is 0, 0 plus 1 is 1, y equals 1, and we get this point here. So you can see that the perfectly horizontal line starts to take shape when we plug in different values for x. So you can prove it to yourself that way also, but just remember that these are special cases where if you have x equal to some constant, it's a vertical line through that number. If you have y equals some constant, it's a horizontal line through that number. Otherwise, if you have both x and y involved in your equation, then you can put it in slope-intercept form and sketch the graph that way, or you can always find coordinate points that satisfy the equation, plot those, and then connect them to form the line.